Let's talk about timing. How fast can our clock run for a sequential circuit? So the timing of a sequential circuit depends on the flip-flop timing and the combinational logic between the flip-flops. A flip-flop samples D at the clock edge, so D has to be stable when it's sampled. Similar to a photograph, if D is moving when we're sampling it, then we may not get a 1 or a 0, but we get some intermediate value, right? If the clock transitions here, oh, that's a problem, right? It's like when someone is moving during your picture, and you just get a blur. You're not sure were they here or there. You actually didn't care exactly, where they were. They were, 1 inch over or where they actually were, but you'd like it to be stable, to stay in that position. So the input timing constraints of a flip-flop on D, so our D input here, are such that, well, around that clock edge, a setup time before that D has to be stable. So these hash marks are saying D can change anytime here, but a setup time before the clock edge, so here's T setup, D has to be stable. These lines 1 or 0 mean it could be 1 or 0, but it can't change. It has to be 1 or 0. And it has to stay stable for a whole time after the clock edge, T hold. And if you think about the timing of the flip-flop, well, the setup time is really the time it takes for D to get to that internal node N1. So when clock is 0, clock bar here is 1, and that's that time before this clock edge for D to get to that internal node N1 and be a stable value, to be a 1 or a 0. The whole time is, well, after this clock edge, right, clock goes from 0 to 1. After the clock edge, we have to keep it stable still. D has to be stable for a small amount of time. Clock goes from 0 to 1, starts letting N1 through, but only a short time later, right, there's some delay here to get through that inverter. And that delay is the hold time constraint. So T hold is the delay to basically turn off L1. Is the delay of that inverter to turn it off, to make it opaque. And so setup time is the time before the clock edge. Data has to be stable, not changing. And hold time is the time after the clock edge. The data has to be stable. The aperture time is those times added together. The time around the clock edge, the data has to be stable. So aperture in an old camera, right, the aperture would open and close. And so that aperture time was the time that the image was exposing on the film and had to be, stable. Whatever you were taking a picture of had to be stable. So the output timing constraints of a flip-flop are Q and when can we get that output Q. And so if we look at our picture of our flip-flop, again, 2 back-to-back latches, the left one with clock bar, the right one with clock, so L1 and L2. And we get clock transitioning from 0 to 1, but we don't see Q change immediately. It takes some time, and in fact, the time it takes is the time for that internal node N1 to go through the gates and change Q. And so there's a minimum delay, T, contamination clock to Q, and a maximum delay, T, P, or propagation clock to Q. Just because circuits have a minimum and maximum delay, for example, depending on the temperature and where the chip is, where the circuit is on the chip. So circuits have a minimum and maximum delay just depending on temperature, where the circuit is on the chip, etc. So this delay from the output, notice that it's T propagation clock to Q instead of propagation delay because it depends on the clock edge. Clock going from 0 to 1, not data changing. It actually depends on the clock changing Q, right? The clock is transitioning and causing that internal node N1 to be able to change what Q is. So it's a propagation clock to Q. So propagation clock to Q is the max delay, and T clock to Q the contamination delay, or the minimum delay of a flip-flop. So the inputs to synchronous sequential circuits have to be stable around the aperture time, a setup time before the clock edge and a hold time after the clock edge. So let's consider what the timing is of our synchronous sequential circuit. And this timing, we call it the dynamic discipline because it's a discipline of signals when they're changing or dynamic. So the delay between registers that we can have has a minimum and a maximum delay, depending on the delays of the circuit elements. And so we have a clock edge, and we have our contamination clock to Q changing that output Q1, and that goes through our combinational logic, which also has a maximum and a minimum delay. That could start changing as early as this point because of TCD, right, this TCD, or as late as some later point because of the propagation delay of the combinational logic. And then it has to get to D2, and D2 has to stop changing a setup time before the next clock edge. And so now let's put some equations to what we just talked over kind of at a high level and say, well, what constraints do we have on the cycle time and on any other timing constraints?